Yeah, so we can start now. So I hope all of you are doing well, and still we are going through this COVID pandemic, and again we are meeting online. Fine, but again, uh, this time it's a you can say second time we are meeting right like this. Okay, so let's try to make it more interactive. Okay, and we have learned so many things in many ways, like how to learn online, how to teach online, and all these things were new, very new to all of us. Okay? Right. So I will try to make it more interactive. Okay, and of course your support is necessary, and I appreciate that last time you people were raising doubts and try to get it clarified during the class session itself. And I hope people will continue that as well. Okay, because once the semester goes on, means people will get sit silently, and sometime it happens. Okay, but uh, this is the stage, but where you can where you can ask. Don't bother what kind of doubt you're asking or something. Okay, of course, most of the time it is expected that it should be related with the course itself. Okay? And however, sometimes it happens that you may have some other idea what to get into it with this course. So that can be discussed actually separately if it is only a personal matter. Okay, because sometimes what happened is this is a very I think a third semester course, so maybe sooner you will be going through with I think with next semester or maybe third year onwards, you will be going through some of the project and all. So there you will find out how these things will be applicable in your real life, and that real world problems and so on. Okay, there you will see how they are going to be used. It depends that what is your interest in. Okay, and uh, uh, with whom you are going to work with, and because sometimes people interested only doing pure mathematics. Okay, and sometimes people interest is applying pure mathematics into some real problems. Okay, it depends. Okay, how you are uh, get interested in. Okay, so there are various examples also. Okay, it's like you should not think surprised that okay, how the engineer will be interested in learning only pure mathematics. There are various examples. Okay, right, and let's see. Okay, the course we try to make it more smooth, means than previously, and more interactive as well. Okay, and this course name itself is telling you that what are type of contents will be there. Okay, so it's a functions of several variables, and that's PDs. Okay, so PD is I hope you are now well aware that partial differential equations, maybe somewhere you have cross with this word. Okay, right. So functions of several variables and PDs. So in the previous course, we have learned function of single variable, and then attach a type of nature of the functions. Okay, there means like a limit, continuity, differentiability. Okay, and then Taylor's theorem, what we also see, and how to locate the root of the equation f of x equals to 0 by using bisection method, or it's like Newton-Raphson method. So I'm trying to mentioning these names at this stage itself, so that like you will able to connect that what you have learned previously, that is going to be used here. Other thing is very simple to observe that. So I've talked about the limit, continuity, differentiability of function of single variable. How they are going to be, whether they are going to be, so this is a very general question, whether they are going to be in a different way to several variable case, or it's a direct generalization. Okay, so there are right obvious thinking. I hope there are two only ways what we can, what the people can think. And of course, we have dealt with the ODEs, ordinary differential equations, where we have seen how to decide the order of the differential equation, how to decide the degree of the differential equation. And we have seen that even the second order differential equation with variable coefficient is uh, is not always solvable. Okay, so you have to yeah, depending on the coefficients, right? If you recall, we have looked at some type of power series solutions. So means likewise, suppose so likewise the ordinary differential equation itself has challenging issues. So I think you should so that PD is going to be more complicated. Okay, though they are so PDs are going to model many various phenomena like diffusion, okay, wave equation, and so on. I mean, it's like finding the waves when you vibrating a string. Okay, how they are going to be modeled into a PDs, that we also try to discuss here. Okay, so finite length string or infinite length string, and then what are the what you have acquired the knowledge from the previous study, we try to uh, deliver, I mean, like in a more general fashion here. Okay, right. Okay, so I hope the course code is with you, MC211. Right now, so main lectures I will be going to take tutorials. It depends. Some time teaching assistant. Most of the time teaching assistant will be helping you there, but it doesn't mean that I will not be there. So I will also will be a part of it. Okay, sometime. Right. But so far teaching assistant has not been assigned. So I have put it like teaching assistant here. Fine. Right. So here is the distribution of marks. So it's 100%. So 100 out of 100. So now if you look at the attachment what I have provided earlier, it's fine. So 20% is fine here. Okay, mid-semester exam is 20%. And semester exam, there I have proposed that 40%, but now I have made it to 30%. And I have given more weightage to project. Okay, so that you will be able to relate some real problems with the pure math. Okay, and we come up with, so if you put the weightage more here, okay, then you will be doing serious work. Okay, so that's why at the first class itself I'm making you very much clear that 50% is their, I mean, it's like written examination. So in the project case, it's most of the part will depends on your viva. Okay, report also as well. Okay, but project viva will take care, means I think most of the marks from 30. Okay, I'm telling you at the first stage itself, and this will cover the entire syllabus. Okay, and quizzes and assignments, so you will, as usual, some of home assignments, tutorial sheets. Okay, and I will also plan for some quiz. I will decide maybe sometime later how to make it happen, means like through Moodle or through Google Classroom. Okay, and we will see how we will conduct these quizzes. Okay, so you can make this quizzes and assignment, this is 10 plus 10. Okay, so it's a very early stage where I should define the distribution of mark very clearly. And in the project, okay, so project, it's depends on the problems. Okay, the state. So I'm working over that. Okay, and because see, once you are done, so then if it is going to be a individual thing, like suppose I give you all same problem. Okay, so it is very easy to one will do, other will copy. Many times it will happen. Okay, so I will not give that report to be like that report you have given, that is not going to be weighted much. It's like out of 30 you can expect 10 marks for this and 20 marks for this, or it may be vary. Okay, it depends on your the problem statement. Okay, how many number of problems I will give, or okay, how it is going to be used. Or another idea is why I should give. You can search out some of the problem. Okay, what you can do, you can look at the contents. Okay, that's a inverse problem. This says inverse problem. Okay, so rather I'm going to give a project to you. You may also come up with the sum of the problem. Okay, but in that case, what will happen is somebody will choose very simple problem, somebody will choose a very interesting problem. So it depends then. Okay, so I let me give, let me have 1 week time over to think about it. But one thing sure, I have done this experiment with the other batch as well, and they have come up with the wonderful projects. Okay, so let me think about it, because this is too early. You have in third semester, maybe it is okay. So let me see, okay, about it. But report will not get much weightage than the Viva. That I'm making you clear. Okay, right. Now, the text and reference books are already have mentioned in the attachment. However, here Thomas and Finney, okay, which will explain the function of several variables. Okay, most of the concepts will be there. Okay, and then of course this Siemens book with differential equation, that will explain some of the part of you can say partial differential equations. Okay, we do have the ordinary differential equation also, but we are going to take care of partial differential equation part, right? And that's a very standard book which will cover almost all the topics in the engineering mathematics by Krasik. Okay, so that from there also we will take help. Okay, some other part. So whenever I need to supply some of the portion of the any book, I will supply it, okay, or to the classroom. Okay, right, fine. Okay, so if you have any question regarding the course, if you have, you can ask now, or else we can start with the course. Am I audible, right?
Yes, sir.
Okay. So I think I have made many things clear at the starting itself. Okay. And I think this has been this analysis of function of single variable and ODE we have learned in the first semester. There is a 1 semester gap. Okay. So I thought that let's go for a quick review over it. Okay. And where
Sir,
I'm not going to give you many details. Okay. In the single variable case. Yes.
sir, will the lecture recordings be shared on YouTube or somewhere else?
No, on YouTube only. Okay, but not like the last time. Means I have edited more and more and those things. But now it will be directly go to the YouTube. Okay, and I will share you with your email ID private. Okay, that's only going to be private. Share and will be shared. Okay, is that clear?
Yes, sir.
Okay, so this is going to be as it is on YouTube. That's that is a thing. Okay. So we are going to give a quick review our function of single variable. Okay, means the starting concept, and later on you will try to catch up on the things. Okay, and I means I advise you to reread your concepts analysis of function of single variable and bodies. Okay, means look at your notes. Okay, do at least revise them. Okay, within this week. Okay, and another thing is because the next week there are two holidays, and fortunately or unfortunately they are happening on our class session itself. Okay, Monday and Thursday. Okay, so we don't have any lecture in the next week. Okay, so what I have thought of is this week the tutorial is anyway is uh, meaningless. Okay, and so what we do is this week we will conduct this tutorial as a lecture only. Okay, so next week you will get tutorial. Okay, next week there is no lecture to 2 days, 16th and 19th. There are two holidays in the next week. Okay, so this week Wednesday, instead of tutorial, we will be having a full-fledged lecture. Okay, fine. And I hope you have noted down your timetable as well. Okay, right. Okay. So let's start with this. So I hope you understood. Means like can recall what do you mean by a set? Okay, a collection of well-defined objects and then other operations, union, intersections, and so on. Okay, right. So limit or cluster point of a set. So to define a limit of a function, we require this definition. So I have taken this here as well. Okay. So if you if any point real number, okay, any real number. We are only talking about right now real valued functions. We are not going through complex. Okay. So a real number, we say it's a cluster point. Okay. If you are able to identify a neighborhood, okay, a deleted neighborhood, you can say, okay, such that it contains at least one point of view. Okay, so we say that. So if you take any for every delta, you will be able to find out in deleted neighborhood such that it contains at least one point of view. So if you recall, we have denoted the delta neighborhood of C by this notation, okay, which is the collection of all points such that mod x minus C is less than delta. Okay, so x is in real numbers, set of real numbers, and this is set to be a neighborhood, open neighborhood when you have less than. If you have equal to included, it's a closed. Okay, now we say that C is a cluster point. If you take any delta greater than 0, okay, you will be able to identify a neighborhood of C such that it intersects with A is it's non-empty, or you can say contains, it's going to be, I can say, non-empty. Okay, and what do you mean? I should not say non-empty. This is wait a minute. I should make it very clear. So delta neighborhood minus this C, this deleted. So C point is deleted. So this set intersection with A is not. That's it. Final. Okay. So for every delta, there exists a neighborhood, or you can say deleted neighborhood of C, which contains at least one point. If it is non-empty, at least one point A is there, and which is not equal to C. Okay. So if you design delta equals to 1 by n. Okay. I'm taking you back there. Okay. So if you replace delta by 1 by n, so for each n, you will be able to get a point in A. Okay. Such that this intersection is non-empty. So each point, for each n, you will get one xn, and that will give you a sequence. Okay. And we have also showed that sequence, the generated sequence, is going to converge to that limit point C. Okay. So C may or may not be the part of A. Okay. That's what we'll take. So limit point may or may not be the part of the set. So this is another definition, okay, of defining a cluster point, that a C is a cluster point of A if you are able to identify a sequence xn in A such that limit of xn is C, okay, where each xn is not equal to C. So of course, because of this design, xn is not going to be equal to C, because C is a cluster point, so you will be able to identify a point which is not equals to C, but it's a part of, okay, in the common. Okay. Right. I think that is enough about the cluster point, right? Now, so this is here is what I have said just now. So a number C is a cluster point of a subset A. If and only if we are able to identify a sequence in A such that limit of an is C and an is not equal to C for all. So you can look at the set A is equals to 1 by n such that n belongs to natural number. Okay, and we have seen that 0 is a limit point or cluster point of the set. Okay, right. So you can verify that, okay, from your previous notes that already has been discussed. Okay, right. Now, limit of functions we can define. So a function is defined from the set A to set of real numbers. Okay, A is a subset of real line, you can say real number. Okay, now we say that a real number L is said to be a limit of f at C. Now, what is that C? C is a cluster point of A. That's the very first thing. Okay, if C is not a cluster point, we are not talking about that. Okay, so for a function f, a real number L is said to be a limit of f at C if given any epsilon there exists so and so. Okay, so we have also seen this is in other words, it can say that f of x approaches L as x approaches C. Okay, this is another way. So as you take x with whatever epsilon you will take, you will be able to identify a delta such that mod of f of x minus L is less than epsilon whenever this happens. So since C may or may not be the part of the set A, so there, that is why here the point C is not included. So we have seen the deleted neighborhood. Okay, so for every epsilon, this thing should happen. Then we say that limit x tends to C f of x is equals to L. Right? So C is a cluster pointer. Okay, and f is defined from the set A to real line. We say that this f of x limit is L if and only for every epsilon there exists a delta such that if x belongs to A and 0 less than mod x minus c less than delta, then mod f of x minus L is less than. Okay, so if you look at it closely, okay, this is nothing but a neighborhood, right? Neighborhood, epsilon neighborhood centered at L. Okay, so if you recall, this is nothing but you can write down in the definition in terms of neighborhood as well. So f of x is belongs to you have this is v epsilon of L. Okay, whenever x belongs to v delta of c minus. Okay, so if you look at closely, you can write down in terms of definition of neighborhood as well. Okay, right. So C may or may not be the part of the set A because the cluster point of the set may or may not be the part of that. So function may or may not be defined at that point. Okay, so f of c. So in the name definition, okay, it should be clear that function may or may not be defined at that time. Okay, but the limiting value may exist. Okay, right. Now, so if so we can here we have already we can recall that if n is the limit of f at c, we say that f converges. So there are various ways to call this. Okay, I have just now given a symbolic form that f of x is tends to L as x approaches to c. F converges to L at c. F approaches L as x approaches c, and so on. Okay, so these are you can say synonyms of this definition. But another way, right? So if the limit does not exist, we say that f is diverges at c. So if f is converges to L at c, if it does not exist, we say that f is diverges at c. Okay. Right. Now, so some of the important thing which I need to mention, that uniqueness of the limit. Okay. Uniqueness. That is important to learn. Okay. So if f is defined over the set A, okay, and if C is a cluster point of view, then f and have only one limit. So if it exists, it says that the limit is unique. So there is no two different limit. Okay. So we have seen also that proof in the previous session, right? Yeah, another is this is the only definition of in terms of neighborhoods. I'm just skipping it. Okay, so I've already told you. Okay, these two are equivalent. So I think this what is that mean is I have just mentioned. So this definition and this definition both are same. Okay, so that I have just now told you. Okay, right now. Sequential criteria that was also has been used to prove that the limit does not exist. For example, we have also shown that limit x tends to 0, 1 by x does not exist. Okay, that we have shown also by using the sequential criteria. So you can take x equals to 1 by n. We have taken xn is equals to 1 by n there. And we know that limit of xn is 0. The sequence limit is 0. And what are the images f of xn? What is the image f of xn is 1 upon xn. right? Because f of x is 1 by x, f of xn is 1 by xn. So 1 by xn is 1 upon 1 by n, that is going to be n. And you know, the limit of this sequence n is turned into infinity as n tends to infinity. So the limit does not exist. Okay, this we have used sequential criteria in establishing this result, or many other result also, sine of 1 by x, okay, and so on. So f from A to R, let C be a cluster point of A, then the following statements are equivalent. So limit exists implies for every sequence that converges to C, the sequence f of xn converges to L. So what does that mean? If means you take any sequence xn in A which converges to C, this implies f of xn converges to L. Okay, of course, C is a cluster point, so xn is not equals to C. That's true. So if you take any sequence which converges to C, its image f of xn should converge to L. And you are able to identify a sequence here which does not follow this rule, so limit does not exist. So if you are able to identify a sequence which fails to satisfy this condition, means it says that the limit does not exist. Okay, so the sequential criteria is used for establishing the divergence at C. Okay, right, most of the time. Okay, so this is the divergence criteria that's just now I have explained to you. So if you look at this first part, it's very it's again repetition of that only. Okay, the conduct concept. So if L is in R, then f does not have limit L at C if and only if there exists a sequence such that xn converges to C, but the sequence f of xn does not converge to L. So just now I have told you, so if you are able to identify a sequence xn which converges to C, xn is not equals to C in A. Okay, this is in A, xn is not equals to C, is in A. Then if you are able to show that f of xn does not converge to L, that means that limit does not exist. And inverse also true. Okay, right. But sometimes it happens that this limit L is infinity. Sequence f of xn does not converge. Infinity means is if you look at the previous one, here n is infinity means f of xn does not converge. Okay, so if you are able to show that the sequence f of xn does not converge, then also you say that f does not have a limit L. Okay, so this is way of doing writing in a mathematical shape what we are looking at. Okay, right. So so this convergence criteria or divergence criteria both are related. Okay, negation, right? Okay, so we have seen those examples. I'm not going to work over. So this, okay, let me give you one. So this is already done. Okay, signal function, you know, okay, signal function of x is going to be x by mod x, right? Just yes, x by mod x. So it's going to be 1 if x is greater than 0. It's going to be minus 1 if x is not. So you can take x equals to, okay, so x tends to 0. So for that, you can take xn is equals to, of course, minus 1 to the power n by n. I'm taking this. So which tends to 0 as n tends to infinity. Now, what is signal function of xn? Is going to be minus 1 to the power n by, or let's say, write it in more way. I think this example we have seen there, so xn by mod xn. So replace everything, what you will get is minus 1 to the power n. N will get cancelled, mod of minus 1 to the power n is 1. Okay, that division by n will get cancelled. And you know, this sequence is oscillating sequence. Okay, and which does not converge because it will give you for even number n, it will give you positive 1, for odd number you will get negative. It's an oscillating sequence. So similarly for this here you have to make it like again we have created an artificial here. So similarly here also artificial you have to take. Okay, so for this case you can look at what you can do is x equals to 1 upon 2 or 1 upon n pi. Okay, if you take 1 upon n pi, this tends to 0 as n tends to infinity, right? And what about a sine of 1 upon x, 1 upon n pi? So sine of n pi, so that is going to be sine of n pi is just a minute. So we have to create a smartly here. Let's see. So limit x tends to 0, sine of 1 by x. This limit does not exist. And so if you take xn is equals to 1 upon n pi, so you know what is f of xn is equals to sine of n pi, right? So that is going to be 0. That is not going to help you. So what you can do is instead of n pi, you can do what n pi by 2. Okay. Now still it converts. Okay. Still it converts to the 0, and you have sine of 1 upon xn, right? n pi by 2. And you know, sine of n pi by 2, it's pi by 2 is 1 minus, at 3 pi by 2 is minus 1. So it's going to be minus 1 to the power n. Again, you will find the oscillator. So you have to be smart enough to identify the sequence. Okay. Right. So this practice we have done in the last semester. Okay. Right. So now the next definition is when you say a function is bounded, okay, on a neighborhood of C. Okay. So if you are able to, so we see it is see when you talk about a function, it is not possible to talk about locally. Oh, sorry, globally, right? Okay, means over the entire region, if you want to try to look at, means you will lost somewhere. However, if you look at locally, means like in a small neighborhood or in a very small place, okay, or identify a place where you're looking at, then it will be simple. So this is what is identifying here in the definition, that we say that f is bounded on a neighborhood of C if you are able to identify a delta neighborhood of C and a constant m such that we have this. So of course f is defined only at the point belonging to the set A, because f is defined on this A is the domain. Okay, and you take the intersection with that delta neighborhood over which this f of x is bounded. And I hope that is very much clear. You say that function is bounded when you have mod of f of x is less than or equals to m for all x belongs to A. That's a definition over the whole domain set. Okay, now if you want to look at only locally, because this A could be a set of real number, and you want to see whether it is going to be bounded on the interval, let's say -1 to 1, or 1 to 2, or 2 to 3. Like for example, you have f of x is equals to 1 by x. Okay, so if you look at the interval, open interval, f is bounded on a neighborhood of, let's say 0, if you look at. Okay, so neighborhood of 0, you can take -1 to 1 open interval where it is not bounded, right? However, if you look at the neighborhood of 1, can you identify a neighborhood for point 1? If you look at 1, so then you will try to make it 1/2 to 3/2. You will not look at the interval which containing 0. Okay, so I hope that's making you more clear, because if I look at f is bounded on a neighborhood of 0 for this function, it is going to be meaningless. It's not going to be bounded on any neighborhood of 0. Okay, now if I look at f is bounded on some other, on a neighborhood of some non-zero point, so I should try to choose a neighborhood carefully. So I have chosen this neighborhood carefully 1/2 to 3/2. Okay, if I talk about the neighborhood of 1. Okay, instead I could have chosen that -2 to 2. Why don't I have chosen? Because it includes 0, and you know that at near 0 the function behavior is unbounded. Okay, so right. Okay, now so it's why it is important is if you have a limit, then f is bounded on some neighborhood of C. So to show that it has a limit, then f is bounded on some neighborhood of C. If you are able to show that f is not bounded in any neighborhood of C, that will show that establish that function does not have a limit. Okay, so this is what you have to look at inverse way. So this f has a limit, then it should be bounded on some neighborhood of C. If it does not have limit, means what? If you try to use the negation, means if you are able to show that function is not going to be bounded on any neighborhood of C you consider, it is still remain unbounded, then f does not have limit. Okay, right. Okay, so this is the definition. How will you define the sum of two function, difference of two function, product of two function, scalar multiple, division? Okay, so I hope that is that's clear. Okay, right. Now, so now sum of the limit and all. So this algebra of limits, you can see. So f and g be functions on a to r, and let c be a cluster point of a. Further, let b belongs to r. Then suppose limit extends to c, f exists and equals to l. Limit extends to c, g exists and equals to m. Then sum will goes to sum of the limit. Difference will goes to the difference of the limit. Product will goes to the product of the limit. Scalar multiple will goes to scalar multiple of the limit. Okay. Now, if you talk about the quotient function, you have to make sure that the denominator should not get vanished over the set A, and its limit also not. Then the limit also going to be the quotient of the limits. Okay, that we have seen. Okay. Now, that's another very important result. If you suppose be able to identify the following. F of x is lies inside this closed interval. Okay, you take whatever the point inside A, of course, which is not equals to C, because C is a cluster point of A, so C may or may not be the part of A. So that's why here x is not equals to C is significant. If it is a part of A, it does not significant. Okay, right. So if you have f of x in such fashion, if you have lower bound as well as upper bound. Okay, then, and if suppose the limit exists, then its limit value is also going to lie inside this interval. Okay, and that's a very looks like obvious, but it's not obvious to prove. We have seen that in the last section. Okay, right. So, but what is important here is if the function is lies inside this closed interval AB, and if the limit exists at C, okay, then its value is also lies inside this closed interval. So you can identify the location of the value. Okay, right. Another important result was squeeze theorem, that Cauchy's, or you can say it's not Cauchy, it's going to be sandwich theorem. Okay, means if you have three functions f, g, and h satisfies the following. For every x in A, you have the following relation. So f of x less than equals to g of x less than equals to h of x. Means over the set A, if you look at the geometrically, means f of x lies below the g of x is lies below to the h. Means those curves. Okay. And suppose this limit of f x tends to c exists and equals to L. Limit of h as x tends to c, that is also exists and equals to L. So both limit exists and they are equal. Then it makes sure that the limit of g exists and that is equals to. Okay? So this is how the sandwich theorem is. Right. Now, that's okay. That's a very important result that we have seen. Okay. That suppose the limit is greater than 0. Okay, limit x tends to c, f exists and this is greater than 0. Then you will be able to identify a neighborhood of c where f remains positive. Okay, that's a very interesting result. Okay, suppose the limit value as x tends to c, f is negative. Similarly, you will be able to identify a neighborhood of c such that f remains negative over that neighborhood. Okay, neighborhood means that of course it's going to be intersect with A. I can't talk about without the points where the function is not defined, but you are able to identify it roughly. I'm talking that if the limit value as x tends to c, f is greater than 0, then you will be able to identify a neighborhood over which the function remains positive for all x in the intersection. Okay, right, and that is expected. Okay? Right. Okay. Now we can define the continuity. Okay. So as previously, we are just repeating the same thing here. So A is subset of R, F is from A to R, and let C is in A. We say that F is continuous at C if you have the following. So you can see that there are two changes. The function is defined at C and L value is f of C. And another thing is here, if you look at the limit case, it was 0 less than. Now it is equals to. Okay? Because, why? Because it is C is inside. So these three are the differences here. So first thing is C belongs to A. We're talking about the points which are the part of the domain. Okay, and you say that f is continuous at C if given any epsilon, you have everything is same. You have f of x is going towards f of c. F of x is approaches to f of c, or f of x converges to f of c whenever x is approaching to c. Okay, so x is now equal to c as well, not equals to c as well. This is the entire data. Okay, so if f fails to be continuous at C, then we say that f is discontinuous at C. Okay. Now, we have seen this. If C is a cluster point of A, then f is continuous at C. So, if C belongs to A and it is a cluster point of A, then f is continuous at C if and only if this happens. So, just now, I have identified that L equals to f of C. Okay, so that's the same thing, right? Thus, following three conditions must hold for f to be continuous at C. First thing is, I told you f must be defined. Limit x tends to C, f of x must exist in R. The two values f of C and limit x tends to C, f of x must be equal. So this is justified as the limit value should be equal to f of C. Okay, and C is a cluster point of A, then f is continuous at C if and only if this happens. Okay, right. Okay, so if C is not a cluster point of A, we have identified, okay, in the last session that the nature of the function is continuous at that point. So we at that point, which is not a cluster point of A, the nature of the function is obviously continuous. Okay, there is no other. Right. Now, that this sequential criteria is again the similar generalization now, replacing L by f of C. Okay. So if your every sequence xn in A that converges to C, the sequence f of xn converges to f of C. If you are able to show that, then f is continuous at the point C. Okay, right. Now we say that f is continuous on the set B. So just now we were talking about at a point. Now we are talking about on the set. So means it is a direct generalization if and only if you have f is continuous at each and every point of the set. If it is continuous at each and every point of the set, we say that it's continuous on the whole set B. If it is continuous at each and every point of A, we say that f is continuous. Okay, A is silent. Right. Okay. So now sum of two continuous function, a difference of two continuous function, product of two continuous functions, scalar multiple of a continuous function are continuous. Similarly, if you have for the quotient h is continuous at C, and if h is not vanishing, then the quotient is also continuous. Okay, so if f is continuous, its mod function is also continuous. Mod of f of x is also continuous. Okay, so these are the results which we have on composition of continuous functions. So if you want to talk about the composition of G and F, okay, I have G of f of x. I want to see the continuity at, let's say, C. Okay, so for that, what you require, G compose f should be continuous at C. For that, what is required is f is continuous at C because f is f of x. Okay, so f should be continuous at C, G should be continuous at f of C. Okay, then if you look at inverse way. Okay, so f is continuous at C and G is continuous at f of C. So then if you say the composition function is continuous at C, that's what is here. F is continuous at a point C and G is continuous at a point B, which is f of C. Okay, then the composition is continuous at C. Okay, that f of C should be part of this domain of G. That's obvious because G is only defined over that side. Okay, right. And this is highly applicable when you talk about the continuity of e to the power x square. Okay, so like you can talk about sine of mod x. Okay, so similarly you can talk about you have this is cos of, you say, x square plus x plus 2. So this argument is continuous, cos function continuous everywhere, so this composition is also continuous. You can argue with this composition theorem. Okay, right. Now continuity on intervals. So like in the limit case, we have talked about the f is bounded on a neighborhood of C. Okay, so we say that here this function is said to be bounded on A if there exists a constant m such that, that's a very useful definition, it's entirely bounded. Okay, right. Now on interval, what we have seen, the nature of the continuous function. If you have a closed interval, the function is bounded and its maximum and minimum both will attain. Okay, that we have seen boundedness theorem. Okay, so this is what we said. So let I is a closed interval AB be a closed and bounded interval, and let f is continuous on I, then f is bounded on I. Means its lower bound and upper bound both will exist. So what is the negation of this definition? But that also we have discussed that session, that function f is not bounded on the set A. If given any m, you will be able to identify a point in A for which mod of f of xn is greater than that. That we have already looked at it. Okay. The negation of this definition. Okay. Now, this is a very important result. I just want to recall, that's called intermediate value theorem. Okay, which assures that if a function is continuous on an interval, okay, and if you take any point between f of a and f of b, so we have taken any point, 2 points in I, okay, and you take images f of a and f of b. If you take any point in between them, you will be able to identify a point in that means between a and b such that f of c is a. Okay, so values whatever lies between f of a and f of b, okay, that will be assumed by the function f at some of the point. Okay, right. So this is our intermediate value. But what is the necessary thing is f must be continuous, okay, and I be an interval. Okay, this conditions are required. Okay. Now at the last we want to look at the differentiability of function. So let I is an interval, let f is function defined on this, and let c belongs to I. So we say that a real number L is the derivative of f at c. So how we would define is f dash of c, okay, denoted by this. If what will happen is, if you have this limit of this exists and that is equals to f. Okay, so f dash of c, if you look at back, that's going to be limit of x tends to c, f of x minus f of c divided by x minus c. If this limit exists and that is equals to L, then we say that f is differentiable at c. If f is fails to be differentiable, we say that f is non-differentiable at c. Okay, so this is the equivalent definition what you have learned in the limit case. So it's the equivalent definition in epsilon delta. Okay, right. Now the differentiability implies continuity. Okay, so if f is a differentiable at c, then f is continuous at c. That we have seen the result. And but converse need not be true. F is continuous, but it may or may not be differentiable. So very famous example is absolute function, modulus function, which is continuous and differentiable everywhere. Okay, except at the point 0. Okay, so it's continuous everywhere. Okay, so this function is continuous on R, wherever you take. Okay, in particular, it is continuous at 0. This implies mod x is continuous at 0, but it is not differentiable. Mod x is not differentiable at 0. And if you look at this limit, okay, that limit x tends to 0, okay, that's f of x minus f of 0 divided by x minus 0. Okay, so that's going to be limit of x tends to 0 mod x by x. And if you recall, it's nothing but the signum function. And we have seen how we have proved that this limit does not exist. Okay, by looking at the sequence. Okay, or you can show that left hand limit is x tends to 0 minus is minus 1, x tends to 0 plus is 1. So limit, both are limit does not match. So you can also say that the limit does not exist. Okay. Now this is we have learned already. So we have let f at g be functions that are differentiable. Then if alpha belongs to R, then the function alpha f is also differentiable, and its derivative, you know how to evaluate. Similarly for the sum and difference and product. So for the sum and difference, you will follow the linearity. Okay, means you individual derivative and then perform the sum or difference. But for this product, you have the chain rule. Okay, product rule. Okay. So product is f into g, means f as it is g derivative plus g as it is f derivative. Okay, at C we are talking about. So this is product. Okay, now thus for the quotient function you have the quotient rule. Okay, if g of c is non-zero, then the function is differentiable at C. And you know this quotient rule is. And that composition function what we have learned. Okay, that function, so you can say that likewise we have discussed, right, for continuity at C for this. Similarly here, f must be differentiable at C, g must be differentiable at f of C. Then g composition f is differentiable at C and its derivative is going to be used as chain rule. First g derivative into the argument derivative f dash of C. Okay, so right. Okay, so that's Taylor's theorem. Okay, that's the end of our this revising the concept from the single variable cases. Okay, let me state that. So let n is a set from the set of natural number. I is a closed interval AB. F is defined on this interval I. Okay, so suppose its n derivatives. Okay, suppose f is n time continuously differentiable. In other way, I can say that in that way. Okay, means n time continuously differentiable means it's you can differentiate n time and its nth derivative is continuous. Okay, and that n plus 1th derivative exists. Then, okay, if x naught belongs to I, then for any x in I, there exists a point C between x and x naught, so and so will happen. Okay, what is in general it is doing is f of x is approximated by a n degree polynomial. Okay, whose error term is this. Okay, because you are going to approximate a function by an n degree polynomial. Okay, there will be some error. What will be the error? That will also be given by Taylor's result. Okay, and so this was the application of mean value theorem. Okay, so that we have seen in the last session. Okay, right. So these terms you can have. This is this together. This is we have denoted by Pn of x, and this error term is denoted by Rn. This remainder after you can say n terms. Okay, Lagrange form of remainder. Okay, so you can expand this up to nth derivative and then remainder involves the n plus 1th derivative. Okay, so fn plus 1th derivative should exist on the upper interval AB. So C is the point between x and x naught. Okay, right. So this is what the Taylor's theorem gives you, that it's going to give you an approximation of a function in terms of polynomial. Okay, and then suppose this remainder term, and we have seen that if this n plus 1th derivative is bounded, okay, if n plus 1th derivative is bounded, this remainder will tends to 0 as n tends to infinity. Okay, means if you keep on increasing the degree of the polynomial, okay, the error term is going to be decreased, okay, and decrease to 0. Okay, so this is what known as remainder estimation theorem. Okay, right. So that we can now we can stop here. Okay, what is the time? It's yeah. So if you have any question, you can ask. Yes? No questions? Okay. How much time you have now? Okay. Okay, we will start with the new topic in the next session. Okay. For 7 minutes is there. Okay. Fine. So if you have any doubt, you can ask.